All right, a little bit of two-dimensional motion. That should be old hat, and this is generalized to more dimensions than just two. But we have position, velocity, and acceleration now being vectors, unlike with SLM, straight line motion, where it would just be plus or minus values, plus x minus x, plus y minus y. Now we have to take into account components. So in general, we have the vector r for position. That could be multiple dimensions, velocity and acceleration. If we have the acceleration parallel to a velocity, what does it do? It increases the speed, and that's it. So here is our initial velocity, and we add a change in velocity, which is an acceleration times time. Same direction, the result is a final velocity, which is initial plus at. If a is anti-parallel to v, it decreases the speed, and that's it. So here we have our initial. Here we have an anti-parallel acceleration, change in velocity in the opposite direction, resulting in a final velocity. That's a little bit less. So what happens if the acceleration is perpendicular to the velocity? Well, you know, it changes the direction. And that's it. It's not going to change the speed. So here we have a arc. Here's an initial velocity, and if at all times the acceleration is in this direction, which means if it's an object with mass, it's going to have a force in that direction. It's going to cause the motion subsequently to be in a different direction to produce a smooth curve. So later on, here is the velocity. It's the same magnitude in a different direction. If a is at some angle with respect to the velocity, maybe not parallel to it nor perpendicular, but somewhere in between. So between 0 and 90 degrees, well, you know, it's going to do both, change the speed and the direction. So here we go, initial velocity. Add this vector, delta v is at a different angle, and it's just vector addition. Initial plus change equals final. Let's move on to the equations for projectile motion. So we have independent x and y motions here. The dimensions of x and y do not affect each other. They are independent. So you'll recall that, and that's very important. It's nice because you can treat them independently. You don't have to treat them together, and so it simplifies the analysis. The initial conditions. Usually we launch something at an angle with a velocity v. Given that that's the initial condition, then we can break that down a little bit. The initial vertical velocity is v0 sine of phi. The initial horizontal velocity is v0 cosine of phi. That's constant, and you know why? Because there's no acceleration in the x direction, with the simplifying assumption that air friction is negligible. The acceleration in the x direction is 0. That's what I just said. And the acceleration in the y direction, well, that is negative g. It's the value of the gravitational field of Earth pointed down. Down is negative direction. The vertical motion equations. Well, we just said ay is equal to negative g. Vy is vy0 minus gt. We've developed these before, so I'll just list them. The average vertical velocity under uniform acceleration, the initial plus final divided by 2, so that's the average. The vertical position, y0 plus vy0t minus 1/2 gt squared, and then vy squared is vy0 squared minus 2g delta y. So these are important, and horizontal, as you know, is very simple. We just have that ax is 0. That's a concept. Vx is Vx0, is Vx1, Vx2, Vx3, any intermediate value, constant. The position x is just what it was, plus this constant Vx times t. And those are the projectile motion equations. Let's now do an example considering the flight of a baseball. Let's find some physical parameters here. So here is a fine baseball player smacking that thing, and it makes a nice parabolic trajectory, and it lands on the ground. So we have an initial velocity, 37 meters per second at 53 degrees with respect to the horizontal. We're going to ignore the height of the batter for this first example. It's pretty much a simplifying assumption. That'll help us. The basic ideas here. Then we have a range. So let's find at 2 seconds the position and velocity. And find time for the maximum height and find the max height. How high does that ball go? And then the range of the ball. That sounds like fun. Let's go after it. Okay, at 2 seconds, let's find the position and velocity. The items we are going to need are the x position, y position, x velocity, and y velocity to fully specify the position and velocity. So, x at 2 seconds, initial plus vx0 times t. Well, there is no initial position. It's 0. So it's vx0, which is v0 cosine of theta, theta 0 specifically, because that angle changes as well, times t. So 37 cosine of 53 times 2, 44.5 meters. Y at 2 seconds, put it into the y position equation. But there is no initial vertical position. We're going to call that 0. I do that generally anyway. Wherever we're at is 0 vertical position. So it's v0 sine of theta 0t minus 1/2 g t squared. All right, plugging in the numbers, 37 sine of 53 times 2 for time, minus 4.9 times 2 squared, 39.5 meters. Vx, v0 cosine of 53, 22.3 meters per second. Vy, now Vx was, just a constant value, but we didn't have to, it wasn't time dependent. Vy now is time dependent because it's under the acceleration of gravity. So Vy0 minus gt, Vy0 minus gt, 10 meters per second. All right, the magnitude of the velocity, square root of the sum of the squares, 24.3 meters per second. The angle, inverse tangent of 10 over 22.3 is 24.1 degrees. Let's now express our answer in AP Physics format, namely unit vector notation. V is 22.3 meters per second I plus 10 meters per second J. And now, time to the maximum height and the maximum height. Well, we know that at the maximum height, its vertical velocity is 0. And we know the formula for vertical velocity. It's Vy0 minus gt. Well, that makes it real simple. The time to get to the height is Vy0 over g, which is 37 sine of 53 over 9.8 is 3 seconds. Now the height that it gets to is the maximum value of y. But the formula for y is this, y0 plus Vy0t minus 1/2 gt squared, y0 is 0. So now that we know the time, we can just plug it in. 37 sine of 53 times 3 minus 4.9 times 3 squared, 44.5 meters. Look how easy this is. Okay, the range of the ball, simple, always valid approach. Range is the time of flight times the horizontal velocity. Horizontal velocity is a constant. Time of flight to go up and down, denoted by this up-down arrow. All right, that's twice the horizontal velocity times the time to go to the top of the flight, which we've already solved, right? So it's 2 times 22.3 times 3 seconds, 134 meters. Now we normally solve directly for t and then plug it into the range equation. So here's our vertical position. Well, now it begins and ends with 0. So it's Vy0 t up and down minus 1/2 gt up and down squared. Now in general, this will give you a quadratic equation. And in this case, 0 solves this problem, and so does 6 seconds. So range is Vx0 times time up and down, which is 134 meters. Woohoo! The time for y to be negative 75 meters, so the ball has plunged into the earth, busting its way through the Well, the top part of the mantle. Not the mantle, the crust. Pretty rough going there, but nevertheless, that's beside the point. So here's our position equation. We know the position vertically. It's minus 75. And we want to solve for the time. This is the equation we want to use. y0 is 0. We know where it is. So in any case, we rearrange this into a quadratic format here. And we can now say that time is negative b plus or minus the square root of b squared minus 4ac over 2a. All right, let's plug the numbers in. There's all the numbers. You can validate. Let's simplify what's in the radical. There it is. Gives us the two results for time. Negative 1.92 seconds, 7.96 seconds. 7.96 seconds is the time after it was launched, where it plunges down into the Earth. Negative 1.92 seconds is the time before it was launched, where you would have to be under the Earth, namely 75 meters down, so that when it got to the surface of the Earth, the resulting motion of the ball would be the same as it is in actuality. Make sense? Awesome. Circular motion, uniform speed. Here we have a circle, and here's our circular motion speed, which is constant. Well, it's got radius r, that's a vector quantity, and so is the velocity for that matter. And we have a vector acceleration pointing in, centripetal acceleration. The circular motion speed is distance divided by time. Distance is 2 pi r going around the circle, divided by the period, the time to go around the circle, which is the period, so 2 pi r over t. Now, v is to r as acceleration is to v. All right, we discussed that before, but basically both go through 2 pi radians. Both v and a go through 2 pi radians, as does r. So there's a correspondence between v and r and a and v. So we can say that just like the velocity essentially goes through 2 pi r of change in t, the acceleration goes through 2 pi v of change in time t. That doesn't make sense, then don't worry too much about it, but we have that t can be resolved to be 2 pi r over vc, and therefore a sub c is equal to 2 pi vc over the period. So we're going to sub in this down here, and that gives us a lot of cancellation, but not total, v squared over r, which is also 4 pi squared r over t squared. You will recognize these values for the acceleration of circular motion. And the last part of this little segment will be comments on relative motion. So we have a very wonderful flattened Earth with Deerfield High School sitting there somewhere around Deerfield, Illinois. And we have, coming in from the right, the airplane of physics. Well, define P as being plane, A as being air, E is earth. And here we have a vector quantity, namely the velocity of the air. So here's the velocity of the plane. So we have v plane, v air. And what we're kind of interested in is the velocity of the plane with respect to Earth. So an observer here in Deerfield, gazing up at this wonderful airplane, wishing they could be in it, especially flying it over the Wrangell Mountains of Alaska. What is the motion of the plane from the point of view of an observer on Earth? The way the relative motion vector equation works is, very simply, if it's plane with respect to Earth, then we need plane with respect to air plus the velocity of air with respect to Earth. When we write it this way, we'll notice the outer subscripts match the question we're looking for, which is plane with respect to Earth, PE, PE. The two A's, the air, are kind of like placeholders. They basically cancel out. I'm not sure if that's a good way to say it, but that's how you can think about it. So we have these two vectors, plane with respect to air, air with respect to Earth, and the addition of those is the answer we're looking for, the velocity of the plane with respect to the Earth. There you go.